Hi there, Mindsetters. Welcome to Mindset Learn Extra Live with me, Atiq Mohammed, and in studio with me is Khatleho. I hope you have your pens and pads ready for an informative session of physical science, grade 11s. Don't forget to post any questions that you have on our Facebook page, which is www.facebook.com/learnextra.
Awesome. Are you ready for like a great show?
Definitely.
I hope you guys have stretched as well. And what are we doing today, Atiq? Do you have any idea?
Not sure. Let's ask John.
I think we should ask John. John?
Hi guys, great to be with you today. Now this is a surprise. I'm not usually here on a Tuesday today.
Yes, Tuesday.
But unfortunately Tracy had a little accident, so I'm standing in for her, and we're doing Newton's second law. So
Awesome.
I'm really looking forward to it, and hope you've got yourself sorted out. Remember, to get the most benefit out of these lessons, you need to get the notes beforehand and try the examples. Tracy prepped a whole lot of questions for you, and she included some of the answers. So if you didn't get them, make sure you get them now. Okay, shall we jump in and get going?
Jump into it, yeah.
Okay, right, let's get going. And guys, if there's anything, just stop me and we'll chat it through. So the first thing that I want to talk about is, what are we going to do today? We're going to be taking a look at verifying Newton's second law of motion. So we're going to look at Newton's second law. We'll look at the experimental apparatus. Now, unfortunately, we won't be able to do that in detail, but the calculation bits and the analysis of the results, I'm going to take you through that. And then the next thing we're going to do is we're going to use Newton's second law to solve a whole lot of different problems. And there's some interesting problems. Now, I don't know if you know, guys, Kat, does it make a difference if you stand on a scale
Yes.
in a lift,
Yes.
whether the lift is going up or down?
I don't think it matters.
Do you think it matters?
No.
Oh, well, we'll have to have a look and see. The other question, what do you think out there, learners? How about posting your answers to that lift challenge question to
I
think
think
about?
that is a challenge question.
Do you think
John.
that we could ask that
Yeah,
question?
I think that's a
And let's get some response. Does it matter if you stand on a lift and you stand on a scale, will the reading on the scale change if the lift is going up or if the lift is going down? Here's another little one that we can throw in together with standing on scales. I know how people, at the beginning of the year, they have all sorts of ambitions to get trim and to get fit, and they often stand on scales. Does it matter if your scale is perfectly flat? If your scale was leaning on an incline, would it matter? Would the reading be correct, or wouldn't it? You think about those ideas. Those are some of the types of problems we're going to be talking about when we apply Newton's second law. Right. But let's get straight into it, and we're going to be looking at Newton's second law. And when we do the investigation of Newton's second law, what we're asking is the following. We're saying, what's the relationship between the acceleration of an object and the force applied? Is there any link between them? And so we have to start thinking about that. Now, just remember that last week we covered a little bit about Newton's first law, which says the following. It says that if an object doesn't experience a resultant force, so there's no resultant force, then it will be in equilibrium, it will remain at rest, or it will be moving along at constant velocity. So when something accelerates, we're saying it's either speeding up or it's slowing down. And we want to try and match those two together. The idea of resultant force and speeding up or slowing down, acceleration. So how are we going to do it? And here's the apparatus that you will use. You would use something called a ticker timer. Now, a ticker timer is a little box, and it's got a little needle on it, or a little pin on it, and it bounces up and down. Okay? It's a very accurate timing device. In fact, that timer bounces up and down 50 times in 1 second. And so every time it bends down, it strikes a little pad that's got some carbon paper on it. And that pad makes a dot on some paper. Now, if you allow, like this diagram shows here, attach the ticker timer. There's the ticker timer. It's just a little square box. And you put some tape on the end of it, called ticker tape. It's just a strip of white paper, a little thin strip of paper. And now you feed it through. We attach it to a trolley and allow the trolley to move down a slight incline. then what's going to happen is that the little timer is going to make little dots on the piece of paper. As it moves, it's going to make those dots the same time interval between them. But you know what? As this trolley moves down, we're hoping that it speeds up. And we can adjust that by adjusting a different applied force. So this will be the force that we apply, a little mass piece. We know it's going to experience a force downwards, the force of the earth pulling it downwards, which is going to cause this to run down the slope. Okay? Hope you've got the setup. Hope you understand exactly where we're at. Now you might be saying to me, why is the slope at an angle? Why do we bother to have it at an angle? And you should remember this from last week, that in fact, any surface has a frictional force. And we want to get to that point where we adjust the slope so that it compensates for friction. So there's no friction that's going to act against the movement of the trolley acting downwards. So that's why we're doing it. We're compensating for friction. So you can read the method in the notes and go through it, set up the apparatus, do the calculate, all of that. Now, what I want to get into is the exciting bit. And that says, after you've run the trolley down, you get this piece of tape. Now what do you do? Maybe you're going to be left in that situation, but how are you going to interpret it? Let's go to the next page, and I've drawn something for you to have a look at. So here's a piece of tape. It's not one from the type of experiment that I've just described. The orange outline represents the tape, and the white dots represent the dots from the ticker timer. Now, what I want you to see is the pattern. This green arrow indicates the direction of motion. So we started at this end over here. This was the starting point, and we've moved the tape, so this is the end. And if you look carefully, and I don't think it will take too much to show this to you, but if you look carefully and you say, well, what's the distance between those two dots? You will see that if we pick those up, the distance between the dots stays more or less the same. The distance between them is not increasing or decreasing. So what is this saying? Remember what I said to you. I said to you that the time between there and the time between there is the same. T2 and T1, those time intervals are the same. We can say T1 is equal to T2. Now, I did mention earlier that that ticker timer goes through a cycle of 50 dots a second. So that means that we can work out what the time is between two dots. Now, you can change the frequency of the timer. You could make it 20 hertz, which means 20 times per second. So you'd be able to work out the time if you know the frequency. Remember from grade 10, frequency and period are related like this. Frequency is equal to 1 over period. So period, the time between dots, is 1 over f. So we can work that out. Each of these time intervals is the same time. They don't change. And what we're saying is that when we've measured the distance between the dots, we found the distance is the same as well. So if we know that the change in position or distance or displacement of each of those intervals are equal, so that's a certain number. It's a constant. It's not changing. And the time is the same. We've got the T1 is equal to T2. Then what can you say about the velocity or speed, which is the change in displacement or change in x position over change in time? Can you see that that tells us that this is going to be a constant? It's going to be a certain number. Now we could plug in numbers, and I'm not going to do that, but what I want you to see is that the trolley or the object here is covering the same distance in the same time. That means it's traveling at a constant velocity. constant velocity. What do we know about Newton's first law? That tells us that there is no resultant, that the resultant is 0 newtons, that it's not speeding up and it's not slowing down. And because it's on a straight track, it's not changing direction either. So what we recognize here is that there is no acceleration. The interval, the speed, the change in position over change in time for one interval is exactly the same as the change in position over time for the next. We have to subtract them, we get 0 acceleration. I want to just remind you what that means. And just go to here. If we had to say what is acceleration, acceleration is equal to the change in velocity over the change in time. And what we've just said now is the velocity is the same. So the average or the velocity of one interval, of interval 1 or interval 2 minus interval 1 is going to be the same. Doesn't matter what it is. It's going to be equal, and that's going to be 0. So 0 meters per second per second. There is no acceleration. Look at the pattern again. There you go. Pattern, equal dots, equal time. That's one example. Now, it's not the example of the Newton's second law, where we did have a resultant force. I want to show you what that one looks like. Here it is. And all I want to establish for you is that you can see, and I hope that you can see this very clearly, shouldn't be difficult, that the distance between there and there is not the same as the distance between there and there. Each time, look how much it's going. It's getting bigger and bigger each time. And in fact, it's increasing more and more. So much so that it's got huge by the end. So what does that tell us? When we get a situation like this, we can say there is an acceleration. How are we going to work out the acceleration? Well, we're going to apply our same ideas that I've just gone through earlier. Let's just have a look at it quickly. We're not going to go into too much detail, but I want to just show you how to do it. So what we could do is we could take the initial position and we could take that position. We could measure that distance. So we'd say that's delta x. We know that that's also in a certain time interval. And we could then also take this one and we could say this is delta x. And it's in a second time interval. This one was time interval 1. This one is in time interval 2. I know that I've used 3 dots, and I've done that deliberately, so don't worry about that. So what am I going to say? I'm going to be able to say that the average velocity here, the velocity or average velocity between these 2 points, is going to be the change in the position over the change in time. And the average velocity for the second bit is going to be, call this 1 and call this 2, and it's still average, and it's going to be the change in position over the change in time. Now, when you've worked out those values, and you can do that by tabulating it and getting it all nice and neat, sorting it out, what do we need to do then? Have we got a way of getting acceleration? Yes, we do. We know that we can say that acceleration, A, is equal to the change in velocity over the change in time. So it takes a long time to get this sorted out, but we can take V1 or V2 minus V1, and we will then take it over the change in time, and we'll be able to work out an acceleration. Now, in this case, because the force was the same, we could treat that at different time intervals. We could use another time interval, we could use that one, and we could check that the acceleration is constant. The acceleration is constant because the force is constant. And we would expect that the acceleration over here, at position 1, at position 2, and at position 3, all of those accelerations are going to be the same. we can tabulate that for that particular force. Now, what's important for Newton's second law is that we get the accelerations and then we plot them. And what we're going to do, just go back to the diagram of the apparatus setup, is we're going to change the force. So we're going to get acceleration and force, and we're going to tabulate that, and we say when the force is a certain amount, let's say 10 newtons, then the acceleration is a certain amount. And we're going to then double the force, and we're going to say what's the acceleration, and go 3 times the force, and what's the acceleration. In the end, you get a whole lot of data that you can then plot on a graph. I want to show that graph to you, and I'm just wrapping this up now so that we've finalized this idea, we can come to a conclusion. So from our ticker tape, we can draw a graph that has our force as our independent variable, the mass pieces that we're going to change, and then the acceleration. From each of those ticker tapes, we'll use a different ticker tape for a different graph, a different reading of acceleration. And what we should find is that we get a straight line. That the force, the resultant force, versus acceleration gives us a straight line. That tells us that the acceleration is directly proportional to the resultant force. Now, there's a second part to Newton's second law that compares mass. I'm just going to give it to you because I want to finalize the statement. And the second part says there's a relationship between the acceleration and the mass, and it says acceleration is directly proportional to 1 over mass. Combine those two sets of data together, and we can get this formula. We can say the resultant force is equal to the mass times the acceleration. You need to know that formula really well. You also need to know how it comes from the experiment. But I think I've gone on a little bit long, and this is quite involved. Just wanted to highlight how to interpret a ticker type. And the most important thing is that you've now seen where it's constant velocity and where it's accelerating. Guys, I think I've run over time, but over to you.
Thank you, John. Guys, we're going to go in for a short break, but before that, Katlego has some...
Oh, yes, I do have something to tell them. You guys are seeing right. This is our Cheetos Simba hamper, guys. This is up for grabs for those random acts of kindness that you guys have been posting on the events wall. Keep posting them, guys, because this prize is awesome. There's a huge bag of chips and more bags of chips inside the bag. There is this notepad, this Cheetos notepad. There's 5 CDs. There's this love CDs for the month of love. There is this Donald CD. There is Kaya CD. There is Malik. And there is Unati, guys. 5 CDs for you guys. There's also this t-shirt that Atik and I are wearing. There's this pen and there's this mindset lanyard. Guys, make sure that you enter this competition because this is a really awesome hamper. Definitely. Are you ready for that break, eh?
Definitely. See you guys in a short while. Take a break, have some water, and see you right back. Hi there, Mindsetters. Welcome back to the show. I'm in studio with John, and we are doing physical science today. Grade 11, Newton's second law of motion. Before I hand you over back to John, don't forget, guys, for your schedules, for your notes, and previous videos of the shows,
Learn Extra, yeah.
of Learn Extra shows. You can find them on learnextra.co.za/live. If you have any questions, please post them on www.facebook.com/learnextra. Over to you, John.
Thanks so much, Atik. Guys, great to be with you. Let's get into some revision now of the actual theory. We've done some of the practical about Newton's second law. Now we're going to just revise some of the theory and get into handling some questions. I'd love to get some questions from you. By the way, Atik, has anybody said anything about that elevator problem?
Yes, I did have a few answers. Let's
okay,
check
we won't take them right now. We'll take them just now. But I just want to make sure, if you didn't get the question, make sure you're interacting on the page. Would it matter if you're standing on a scale in a lift? Who's going to do that? I don't know. But if you were, would it matter If you were going up or down, would the reading change? Would it be the same as if you were standing stationary? We'll have a look at that, hopefully, towards the end of the lesson. Okay, so let's have a look now at Newton's second law. We did a bit of an outline of what the practical experiment was, but I now want to get the full statement. Guys, this is important. You've got to learn the statement. And so let's take it step by step so that we learn the principles. So here we go. We've got Newton's second law. It says the following. It says the acceleration of an object is in the direction of the resultant force. And that's a critical thing to notice, that the acceleration is in the same direction as the resultant force. That's what we need to know. The second thing is the relationship. Now we rushed through that relationship from the graph and from our experiment. We say that acceleration is directly proportional. Guys, that means that you can draw a graph of the force and the acceleration, and it's going to be a straight line passing through the origin. We say acceleration is directly proportional to the resultant force, something like that. And then it carries on to say, and acceleration is inversely proportional to the mass of the object. The way we write that is we recognize that acceleration, 1 over mass, if we keep the force the same, change the masses around, we will also get a straight line. Notice this is 1 over mass. We write it as A is equal to directly proportional to 1 over mass, like that. We can combine those two statements and get the equation statement like that, where F net is the resultant force. The mass is measured in kilograms. Very important that you get your SI units. Mass is always given in kilograms. Acceleration is always in meters per second per second. So make sure you've got that. Now, what we need to recognize is that when we do one of these problems, we're going to need to find the resultant. And often that means you're going to need to sketch a diagram. There are a whole lot of tips in the notes. Make sure you get those and you read through them. I'd like to get straight into a problem. So let's go to problem number 1, question number 1. And here it is. It is taken from a previous exam paper. And this is a really good hint. If you can get some old exam papers, this one was taken as far back as the year 2000, and it was a GDE exam paper. Go and practice them. Go and look at them. It is before the NCS. So if you can get them, all the best to you, and make sure that you go through them. So here's this one. It's not a terribly difficult one, but we need to take note of it. It says a crate with a mass of 50 kilograms is pulled along a rough floor. So bear in mind, we must be thinking rough floor means that there's probably a force of friction by a boy exerting a force of 100 newtons. So there we've got a picture, and if they haven't given you a picture, you need to draw it. 50 kilograms, 100 newton force. Now what do they say to you? They say you must draw a force diagram to show all the forces acting on the crate and label the forces. Okay, so let's do that. The first thing we're going to do, when we do a force diagram, we're going to make sure that we indicate the object. We can draw it as a box, like it is, and we're just going to add in all the diagrams. This is not a free body diagram. Of course, you could just reduce it to a dot, and I like to do that myself. So I'm going to draw a dot to represent the box, and I'm going to say what forces are acting on it. Well, from the diagram, we know that the force applied is going to be acting to the right. So we're going to say this is the force applied. That was the pull of the boy. What else do we know? From this idea here, we know that there's a frictional force, and we can put that in. If you read the full question, you'll see the next question is to calculate its acceleration. So we know that the frictional force is not going to be bigger or not going to be equal to the applied force. In this case, it's going to be smaller. The object is accelerating. What other forces do we know? Always remember that we've got a downward force, the force of the Earth acting on the object, and that's equal to the mass times the acceleration due to gravity. And the last thing that we need to bear in mind is there's the force of the surface, which we're going to call the normal force, and that's pushing up. It's the force of the surface pushing up on the box. So bear those in mind. We've now labeled them. You could do it as a little key and be more explicit, and you could put this down here to say Fn is labeled. This is the normal force. And you'd put down Fg. It's the weight of the object. It's the force of the Earth on the object and the force applied. So give the full answer, particularly if they say label it. It's the pull of the buoy, of the rope, or whatever it was. And then Ff is the force of friction. And there we've got it. Right, let's move on. We work with diagrams to make sure that we're getting it right so that we can do some calculations. Can we see if there's a resultant here? Well, I've already mentioned it to you. Bear in mind that the normal force is the same magnitude as the force of the Earth pulling it down. So the only two forces that are really acting is this one, and they're not equal. So we know that there is a resultant. The resultant will be equal to the force of friction plus the force applied. But before I go and do that calculation, I need to make sure that I understand that there's direction to it, that the force of friction is in the opposite direction to the force applied. So let me write this down and say, for direction, I'm going to say that something that goes to the right is positive. And I'm going to use that sign notation, which means that the force of friction, which acts to the left, has a negative sign in front of it. But let's move on. The next question tells us, calculate the magnitude of the frictional force caused by the floor if the acceleration of the crate is 1,5 meters per second. So there was something different. If we read it, we would have seen that in the calculation. But we've got some important information that we've read off our diagram, and let's make sure that we've got it now. We know from the diagram that the resultant force is equal to the force applied plus the force of friction. And over here, what we're going to say is the force applied, if we look back, was 100 newtons, and we say that's in the positive direction, so it's that. How are we going to find? We need to find, look from the question, we need to find this. So how are we going to find the resultant? Well, we know that they're related to each other, but we also know that the resultant force by Newton's second law is equal to the mass times the acceleration. And they've given us, look, they've been very nice. They've been giving us the acceleration. The important thing here to recognize is that we recognize that this is the direction of acceleration, and this is the same direction of the resultant force, because the force applied is going to be bigger than the frictional force. The frictional force is just going to be a little force that's holding it back a little bit. Okay, so let's do the calculation now, and let's work out what the frictional force is. So we're going to say this is mass times acceleration. This is 100 newtons. This one we don't know. We know that it's going to have a negative answer because it's in the opposite direction. So let's substitute in. We substitute in the values for mass. It was 50 kilograms times the acceleration of 1,5 meters per second is equal to 100 plus the force of friction. Now, remember we're not able to work out what this is. And these are added as vectors, but we'll come to that and we'll see exactly what's happening. 50 times 1 comma 5. Let's do the calculator, even though we can do it in our heads. It's not difficult to do in our heads, but let's use the calculator. 50 times 1 comma 5 equals 75. So we now know that the resultant force, look at this, the resultant force is 75. We know that the applied force is 100. Now guys, this doesn't take rocket science to work out what the frictional force is. What must I add to 100 to get 75? I hope you can see that we've got to add minus 25. Because minus 25 plus 100 is going to give you 75. You can, of course, work it out and rearrange the subject of the formula, and you will get something like this. You will get 75 minus 100, and you can check that that equals minus 25 newtons. Now, you can't leave your answer like that. You can't leave it like that. You've got to say that is equal to 25 newtons opposing the motion, opposite to the motion, Or you can even say 25 to the left. It's better to say opposite, but because we might not have this exact diagram, you might have had to draw the diagram. So I prefer to say in the opposite direction to the motion. It just means it's more general and it's safer to put as the answer. Now, I hope you've got those points. Be very careful as you're going through these type of questions. I think it's time to introduce one more question, and this is one that I know that Tracy has given in the notes, and the answer is there. So I'm not going to go through it in too much detail. I'm just going to highlight it for you because I want to get to question 3 at the beginning of our next segment. So we're told that we've got a force of 10 newtons. It's acting on this system. And what you're asked to do is to calculate the acceleration. Not very difficult to do that. The next part of the question, though, you've got to calculate the force of tension between those two. Just a hint as you're going through this, remember to change this to 0.5 kilograms. It's very important that you work with mass in SI units, and grams is not SI units. You must divide by 1,000 to change 500 grams into 0.5 kilograms. So there is another example of a typical type of question using Newton's second law. But I've got a real meanie coming up as question 3. But for the moment, let's go back to Atik. Atik, are there any comments or questions on the page?
Yes, there are. Makutane answered your challenge question.
Okay, we don't want to give the challenge away just yet. We'll give that to somebody else.
Okay.
We'll get to that shortly. Any others?
No, nothing yet.
Okay, guys, don't take too long about this. I want to know what's happening when you stand on a lift and it goes up. What happens to the scale? When you stand on the lift and it goes down, is there a difference in the reading? Come on, guys, you can give me an answer. I don't just want to hear from Makatani. I want to hear from a whole lot of you. I'm going to be checking the page in the break, so please get on there. Give us some comments. Okay, Atik, I think it's time for a break.
Yes, I think we should take a short break. Guys, remember the breaks are important. Take time, process the information that you've learned. And before we go for a break, there was someone here, Janice Govinder, who says who would like a shout out. So shout out to you and thank you for tuning in. Let's go for that break. See you just now. Welcome back to the show. Those of you that have just tuned in now, you've missed an exciting show on the second law of Newton's second law of motion, which is very exciting because motion is all around us. When we walk, cars driving past, even bouncing a ball, that's motion. So if you have missed the show, you can get the schedules and the notes and the previous videos on learnextra.co.za/live. Over to you, John, again.
Atik, thank you so much. Now, during the break, we were going through some of the comments on Facebook. So before I get into the big problem that I want to leave you with, I want to just go through some of those comments. The one comment was, what is the difference between the acceleration and the resultant force? So there's the graph that I've just referred back to. And what we need to recognize, acceleration is measured in meters per second per second. It's the amount that something speeds up or slows down, whereas the resultant force is measured in Newton. What we've got to recognize is that they're related together. They're different quantities, but the resultant force, the acceleration, is directly proportional to the resultant force. That means that if we double the force, increase the force, say let's start over here, we started at that point, look what the acceleration was. If I double the force, make it there, what's happened to the acceleration? Can you see it's also increased? Now, I'm not using a scale diagram. If I was on a graph, you'd be able to see. If you double the one, you double the other. So they're not the same things. Now, there was another interesting question, and I think it was from Boule, and she said, what you've written down here is that the acceleration is directly proportional to 1 over mass. And that's right. If we took 1 over mass and we took acceleration, we'd get a straight line. But what she wants to know, or he wants to know, is what would happen if I took the acceleration against mass? What sort of graph would I get? Now, this goes to the idea of inversely proportional. 1 over changes it to a straight line. But if it's not a 1 over relationship, it's straight like that, then you're going to get a hyperbola. And it's very difficult to tell, is this curve a hyperbola? Remember, a hyperbola, we'd need to say that mass times acceleration is going to be a constant. And that's where the formula comes from. That's where our formula, the resultant force, because that has to be kept constant for this experiment, is equal to the mass times the acceleration. So I hope that's answered your question. You can see, yes, that when it's acceleration and mass, it is not a straight line. But when it's acceleration and 1 over mass, it is a straight line and it passes through the origin. Okay, right, I've been promising you this big question. Let's get to it. And it's one that is often has come up in the past when this sort of thing was done previously and examined previously. This comes from the November paper that was written in the Northern Cape, 2000, and it was a high-grade question. So we can go and have a look at it. It says, 2 blocks of 3 kilograms each are connected by a rope. There they are. There's the 3 kilogram blocks. They're placed on a frictionless horizontal table. A third block of 4 kilograms, there's the third block, is connected to the others by a light rope over a frictionless pulley. So that's frictionless, as shown in the sketch. So all of that is there. What we need to recognize is that they mark the blocks X, Y, and Z as well. And the first thing they ask us is to calculate the acceleration of the 3 kilogram block marked X. So how are we going to do this? We recognize, first of all, when you get a problem like this, please draw a diagram or take note of the diagram so that you can see what all the forces are that are acting on this object. Now, we're only interested for the block X in the horizontal forces. Yes, I know that there is a force downwards and there's the normal force that acts opposite, but those aren't going to help us accelerate. The thing that we need to remember is that there is no friction. And if there is no friction, that means that the only force that's acting on this block is in fact a force in that little rope that's going to pull it in that direction. So how are we going to work out the acceleration? We're going to say the acceleration is equal to the resultant force divided by the mass. And if we got that, then we're safe. We're altogether okay. So the resultant force on this block, we don't know yet. So we're going to need to just leave it like that for the moment, And we're going to say, what do we know about the resultant force? Well, the resultant force, we just simply rearrange, is equal to the mass 3 times A. And that's all we can say for the moment on that particular block. Let's move to the second part of the question. And the second part of the question says, hold on, guys. We don't just want to know about block A. We want to know what is the tension between X and Y. What is this force over here? Now, let's try and work that out. We haven't answered fully that top question. And I want to get to showing you how to do it by looking at the next question. I just want to get the third part of the question out, was to calculate the resultant on the 3 kilogram block marked Y. And then the last part of this question, that was the last part. So we've got to put these questions together and try and work them out. So 3 kilogram block marked X, we only know at the moment the resultant force. So there are different ways of doing it, and I'm going to make sure that we look at it separately. The first statement that I've got is about block X, and I'm going to say the resultant force on block X is equal to 3 times its mass. Now, what about Y? What about this block? What's happening on Y? Now, what we can say is on Y, look at it, we've got Y over here, we've got a pull that way and a pull that way. So this is the force of between X, Y, and this is the force that I'm just going to say is a force applied. So what we recognize is that there are two forces here. The resultant of those two is going to, that's going to be the resultant. We're going to have to add the one to the other, and we're going to have to get them sorted out. This is the tension in the rope. This is the tension in the rope. And so we're going to say the resultant of this one is going to be, let's keep the force to the right positive, and we're going to say it's T minus Fxy. That's the resultant, and we know that's equal to 3 times, the mass was 3, sorry, the acceleration, I've done something wrong here. That should have been A, 3 times A, because they were both 3 kilograms. They're both 3 kilograms. This one's 3 kilograms, that one's 3 kilograms, and we're wanting to get the acceleration. So it's a bit of a long way around, but we're almost there. The final thing that we're going to do is we're going to say Z. This is this bit here. Now, look at what Z is doing. Z has got the force of gravity acting on it, and it's got this tension that was in the string. And the tension here at this end and the tension there is the same. So I'm going to write up a little equation and set it up. And I'm going to say what I need to know is that the force downwards, the Fg, is greater than the tension because it's moving down, minus tension is equal to 4 times the acceleration. The 4 comes from the mass. And so I've got 3 equations, and I'm going to need to solve these simultaneously. And that's the trick here. You've got to add these together and put them into an order. And that's exactly what I'm going to do. So I'm going to say to myself, I've got the tension between Fx and xy as 3a, and I know that that one there. So I'm going to just substitute that in to this equation. So I'm going to get T minus 3a is equal to 3a, and then I'm going to take this equation here of Fg, which I'm going to write as mg, Fg being mg because it was the mass times the acceleration. So let's just substitute that in very quickly. Fg is equal to mg, which is 4 times 9,8. I need to work that out. So quickly, let's get the calculator and let's get it onto the screen. And we're going to say 4 times 9,8 equals, there's my answer, 39,2. So 4 times 9,8, 39,2. Please remember that, Atik. Don't forget it, 39,2. So the value is 39,2. So if I substitute that in, I can now get some detail going here. I can say 39,2, almost done, 39,2 minus t is equal to 4a. Now, I hope you can see something. There's something interesting happening. I've got two equations. If I add them together, look what happens. If I add these two equations together, I'm going to get t plus minus t. Those are going to cancel out. So that cancels with that. And then I'm going to get 39,2 minus 3a is equal to 7a on this side. And that just simply means that I can expand it and get 39,2 is equal to 10a. Brilliant. So what am I going to say? A is equal to 3,92 meters per second per second. I've got it. I've worked out the acceleration, and that's a critical point. Notice I've used simultaneous equations to do that. I've looked at each of the aspects of the system, and they're not all acting in the same direction, but I've combined them, and I've worked out the acceleration. Atik, are we okay?
Yes, definitely.
Okay, let's move on. The next part of the question now becomes really easy, because I can take either of these two equations, okay, and I can use them to work out. If I know the acceleration, I can work out what's happening in the second part. And that's exactly what I'm going to do. So we want the tension between the ropes. I now know what the acceleration of x is. I know that if you go back there, I worked out that the acceleration, remember, was 3,92. So if I want the tension in the rope, I only have to look at one end. And I can say the tension is equal to the resultant force on x, which was the mass times the acceleration. We know what the mass was. The mass is 3 kilograms. The acceleration was 3,92. And we can therefore work out that the tension is equal to we divided that by 10 to get the acceleration. We're going to multiply that by 3, and we get the answer that the tension is 11,76. 11,76 newtons, and that would be the tension in that rope, and in this case, it is acting to the right. It's the rope pulling on X. Okay. What I'd like you to do is to have a look and see if you can work out that the tension is the same at the other end. It really is. Believe me, you can substitute in and you'll find it is the same. Now, if I know that that's the tension, the last part of the question was what's the resultant force on the 3 kilogram block? Now, let's look at this way. The resultant force is equal to the mass times the acceleration. We know that the tension is in that direction. There's another force in that direction, and we can work out what the resultant force is on the 3 kilogram block marked Y by simply putting in 3 times A and working it out. It's not that difficult. If they really wanted to make it tricky, what they would have done is said to you, what's this tension? Then you'd have to use that and work out to find what that tension is. Guys, these problems take practice. Don't give up. Don't think that because you've seen it and, I don't know what's going on, that you need to give up. Don't. Persevere. Practice. Look at the solutions. They are on the notes as well. I think we've almost come to the end. I think the last thing we need to say is about the scale.
About the stem, yes.
There, the scale. So very quickly, guys, it does matter. If you're standing on a scale and it's going up, then the reading on the scale is going to increase. If it's going down, the reading will decrease. Atik, it's been great being with you.
Thank you, John. It's been a wonderful show. Thank you, Grade 11s, for tuning in. Grade 12s, you are up next. Guys, don't forget to post your random acts of kindness, and you could stand a chance to win this awesome prize by Simba. Thank you, guys. See you same time, same place next week.
When something accelerates, we're saying it's either speeding up or it's slowing down. And we want to try and match those two together. The idea of resultant force and speeding up or slowing down, acceleration. So how are we going to do it? And here's the apparatus that you will use. You would use something called a ticker timer. Now, a ticker timer is a little box, and it's got a little needle on it, or a little pin on it, and it bounces up and down. Okay? It's a very accurate timing device. In fact, that timer bounces up and down 50 times in 1 second. And so every time it bends down, it strikes a little pad that's got some carbon paper on it. And that pad makes a dot on some paper. Now, if you would allow, like this diagram shows here, attach the ticker timer. There's the ticker timer. It's just a little square box. And you put some tape on the end of it called ticker tape. It's just a strip of white paper, a little thin strip of paper. And now you feed it through. We attach it to a trolley and allow the trolley to move down a slight incline. Then what's going to happen is that, or if the lift is going down, here's another little one that we can throw in together with standing on scales. I know how people, at the beginning of the year, they have all sorts of ambitions to get trim and to get fit, and they often stand on scales. Doesn't matter if your scale is perfectly flat. If your scale was leaning on an incline, would it matter? Would the reading be correct, or wouldn't it? You think about those ideas. Those are some of the types of problems we're going to be talking about when we apply Newton's second law. Right, but let's get straight into it, and we're going to be looking at Newton's second law. And when we do the investigation of Newton's second law, what we're asking is the following. We're saying, what's the relationship between the acceleration of an object and the force applied? Is there any link between them? And so we have to start thinking about that. Now, just remember that last week we'd covered a little bit about Newton's first law, which says the following. It says that if an object doesn't experience a resultant force, so there's no resultant force, then it will be in equilibrium, it will remain at rest, or it will be moving along at constant velocity. So when
Hi there, Mindsetters. Welcome to Mindset Learn Extra Live with me, Atiq Mohammed, and in studio with me is Khatleho. I hope you have your pens and pads ready for an informative session of physical science, grade 11s. Don't forget to post any questions that you have on our Facebook page, which is www.facebook.com/learnextra.
Awesome. Are you ready for like a great show?
Definitely.
I hope you guys have stretched as well. And what are we doing today, Atiq? Do you have any idea?
Not sure. Let's ask John.
I think we should ask John. John?
Hi guys, great to be with you today. Now this is a surprise. I'm not usually here on a what's it, Tuesday today.
Yes, Tuesday.
But unfortunately Tracy had a little accident, so I'm standing in for her, and we're doing Newton's second law. So
Awesome.
I'm really looking forward to it, and hope you've got yourself sorted out. Remember, to get the most benefit out of these lessons, you need to get the notes beforehand and try the examples. Tracy prepped a whole lot of questions for you, and she included some of the answers. So if you didn't get, the little timer is going to make little dots on the piece of paper. As it moves, it's going to make those dots the same time interval between them. But you know what? As this trolley moves down, we're hoping that it speeds up. And we can adjust that by adjusting a different applied force. So this will be the force that we apply. A little mass piece. We know it's going to experience a force downwards, the force of the earth pulling it downwards, which is going to cause this to run down the slope. Okay, hope you've got the setup. Hope you understand exactly where we're at. Now you might be saying to me, why is the slope at an angle? Why do we bother to have it at an angle? And you should remember this from last week, that in fact, any surface has a frictional force. And we want to get to that point where we adjust the slope so that it compensates for friction. So there's no friction that's going to act against the movement of the trolley acting downwards. So that's why we're doing it. We're compensating for friction. So you can read them. Make sure you get them now. Okay, shall we jump in and get going?
Yeah, jump into it, yeah.
Okay, right, let's get going. And guys, if there's anything, just stop me and we'll chat it through. So the first thing that I want to talk about is, what are we going to do today? We're going to be taking a look at verifying Newton's second law of motion. So we're going to look at Newton's second law. We'll look at the experimental apparatus. Now, unfortunately, we won't be able to do that in detail, but the calculation bits and the analysis of the results, I'm going to take you through that. And then the next thing we're going to do is we're going to use Newton's second law to solve a whole lot of different problems. And there's some interesting problems. Now, I don't know if you know, guys, Kat, does it make a difference if you stand on a scale
Yes.
in a lift,
Yeah.
whether the lift is going up or down?
I don't think it matters.
Do you think it matters?
No.
Oh, well, we'll have to have a look and see. The other question, what do you think out there, learners? How about posting your answers to that lift challenge question to
I
think
think
about?
that is a challenge question.
Do you think
John.
that we could ask that
Yeah,
question?
I think that's a good
Definitely.
And let's get some response. Does it matter if you stand on a lift and you stand on a scale? Will the reading on the scale change if the lift is going up